Hi everyone, and welcome to the 12th webinar in AWC3's webinar series about watercourse crossings. My name is Daniel Monaco and I'll be acting as the host for today's webinar. So before getting into the webinar today, I wanted to give a brief introduction to AWC3 in case this is the first webinar that you're attending in the series. So AWC3 is Alberta Watercourse Crossing Collaborative. It's a not-for-profit organization whose primary objective is to facilitate information transfer around the issue of watercourse crossings in Alberta and their impact on native fish species. So that's what this webinar is all about. It's sharing information from subject matter experts and trying to get that information out to as many people as possible. So since we've received some questions about this, I just want to let everybody know that the webinar can be used for continuing competency credits for professional associations. So it counts as half an hour of credits and can be approved and has been approved, by most major professional associations. So if this is something you're hoping to take advantage of, please keep your receipts and your registration confirmation email. And if you have any questions about this, you can email us at info@awccc.ca. So today's webinar is about crossing alternatives, applications of an open bottom plastic arch. And we have Ben Poltorak from Earthwork Environmental Strategies with us as a presenter. So to give a bit of a background on today's presenter, Ben has been active in environmental consulting and leadership in the delivery of services to forestry and upstream oil and gas industry coast to coast across Canada since 2003. He has a Bachelor of Science in Forest Management degree from the University of Alberta and a Master of Science in Forest Engineering degree from the University of New Brunswick. Ben has ample experience in forested site reclamation, contaminated soil and groundwater assessment and remediation, spill response, silviculture, engineering, research related to soil science, wetland ecosystems, and has been developing a team of aquatic professionals focusing on watercourse crossing monitoring, mitigation, installation, and restoration. So before passing things off to Ben, if anyone has questions throughout the presentation, you can submit those through the GoToWebinar program. So you'll see a toolbar on the right-hand side of your screen, and you'll be able to submit questions there. I'll be compiling those questions throughout the presentation, and we will get to those after the presentation is done. So the way the format of this works is I'm giving this brief introduction, and we'll have about 25 to 30 minutes of Ben's presentation, followed by about half an hour of Q&A. I'd like to ask that if anybody does have questions, that they keep those questions directly related to the topic of the presentation so that Ben is able to answer those to the best of his ability. So without further ado, I'll pass things off to Ben.
Okay, thank you very much for the introduction there, Daniel. That's right, my name is Ben Poltorak. I work for Earthmaster Environmental Strategies. And today with you, I'm going to discuss open bottom culvert systems for fish-friendly watercourse crossing on resource roads. The intent of this presentation is to provide practitioners and interested parties another tool for the toolbox when it comes to watercourse crossings. This product that I'll go through with some details and some applications and a case study for the installation of this product is one that we've had some good success with over the years. It has been on the market for a number of years. I know the forestry world has been using this product and very similar ones for a few decades now. In other industries, it is a little bit less common, but it is starting to come online and it's starting to be more mainstream. So we'll go through some of this today, and I hope that it comes out useful to everybody who's tuned in today. There we go. Okay, so one thing I've noticed about the webinar presentation so far is that everyone seems to have their own personal collaboration of terrible watercourse crossings that they've seen out there in the landscape. So this is no surprise to anyone who is out there kind of on the ground looking at these things. What it tells me, though, is that there's definitely a problem in our province with regards to this particular topic. Here are a few that I've stumbled across over my time, and I'm sure there'll be many more to come. But how do we get to this state? The question is, how do we get there? Why are we there? And why are we still fighting with this? So let's take a step back a few years and let's think about the origins and the planning stage of road construction. What happens first? Well, to go from point A to point B, a road center line and alignment is characterized, found usually in an office on the desktop or through mapping software to begin with. And then it's followed up with field inspections and surveying. Watercourse crossings are noted and found. And these watercourse crossings, the watercourses themselves specifically, are in a state of erosion. In fact, they have been eroding since the last glaciation, and they're continuously eroding, some at a higher rate than others, of course, as you can imagine. And then once the planning has progressed to the point of new construction, these watercourses again are still eroding, but the construction crews move through bringing subgrade material in, whether it's from a burrow pit or using the ditching method. And that subgrade material is pushed out until you get very within proximity to these watercourses. What often happens is that a culvert or a corrugated steel pipe, a CSP, is basically pushed over the edge, thrown into the watercourse, and construction continues with the subgrade material. Often these projects are fixed fee bids, and time is not had to properly install these watercourse crossings. So right away from day one, we have numerous issues, including inadequate sizing, no embedment of the corrugated steel pipe. Often the equipment traverses or traffics over that structure too early, and you get deformation of the structure immediately. These corrugated steel pipes require a certain amount of compaction on either side of the facility, and this step is often missed, or traditionally is missed. There's often no footings or poor substrate underneath the structure. So right away from day one, the crossing is set up for unfair battle. Let's fast forward to today, where we now have an old road. That undersized culvert has likely led to backed up water and watercourse flow from the watercourse crossing. So what we end up getting is not erosion or natural erosion at our inlet end. We now have a state of disposition where a lot of those sediments are, in fact, falling out of the water column. And I've seen some culverts at this particular spot on the inlet end where you actually have more deposition than you do erosion, and it leads to the blocking off of that structure. The undersized culvert also accelerates the water flow because it is installed at a horizontal gradient that increases water flow. The reduced friction within a corrugated steel pipe accelerates the water, as well as you also have the venturi effect going on during high flow periods. All of this accelerates the erosion at the outlet end of the culvert. And now we have what's called an outlet gap and a hanging culvert, commonly known. Now, this is kind of a simple way to explain some of our downfalls with the road building and road or lack of watercourse crossing maintenance over time. But there are, of course, other issues, including just simple deterioration of the structure. This could be corrosion, depending on water and soil chemistry. It can be accelerated. It could be a lack of maintenance. Wildlife, beavers in particular, are not a friend to culverts and corrugated steel pipes, as well as debris and ice can cause damage to these structures over time. So what are our options? What do we normally do to replace these? Well, the simplest option is to replace the culvert with a corrugated steel pipe. Let's hope we don't make the same mistakes that we did the first time when we built the road. However, these projects in themselves can be as simple as a 2 or 3 day job, or they can be several months in duration, depending on each site and site specific. And again, I'm not going to dwell on the proper installation of a culvert too much here. There have been other webinars that have gone into this in more detail, and they've done a very good job. I'd encourage you to look them up when they're available. But basically, some advice from someone that I've worked on is to ensure that your slope is as close to zero as possible, and make sure you have it properly embedded and, of course, properly sized for the watercourse. What are the other options? Bridges. Definitely install a bridge. Again, there are other concerns with costs and site-specific constraints that may apply, but is another tool in our toolbox. We also have temporary structures like log or snow fills or ice fills that may be applied, again, only during temporary access requirements. And we also have multi-plate arches, which here on the right, you can see in a mining setting in Alberta, which can be applied, again, another option in the toolbox, but there might be constraints. Well, if we take that same arch design and let's reduce it to something a little bit smaller here, maybe with a different material and lower cost and ease of installation, we actually have another tool in our toolbox that we can apply on these resource roads. And here are two pictures of this modular open bottom culvert system we're going to talk about. The product is EnviroSpan. It's built out of high density thermoplastic material. It's designed to be flexible. They call it an open bottom modular culvert system. And just to be clear, I don't work for EnviroSpan or have no affiliation to the company whatsoever. It's just the product that we have used and have seen some really good results with. Goals for our replacement on this particular watercourse crossing are to restore fish passage, emulate natural stream flow, create a natural stream bed, and increase the diameter of the watercourse crossing. With this product, you can get straight sections as well as curved sections, which will allow you to follow the natural bends and curvature of a watercourse. If you are constructing a new road, for example, you can actually utilize these curves and bends to the fullest advantage so that you do not need to disturb the bed or the banks of the watercourse crossing, and essentially cause no ground disturbance near the watercourse, thereby minimizing your impact in the ecosystem. A properly installed EnviroSpan arch is able to accommodate the natural horizontal gradient of the watercourse. Basically, you can install this product on any angle of watercourse as long as the subgrade is able to. The EnviroSpan arch will stay there and in place. So basically equivalent to the angle of reoppose, so to speak. The bottom or underside of the arch allows you to emulate the natural stream bed if you need to recreate it, if you're removing a corrugated steel pipe, for example. And we'll go through each of these items, including the footings and the placement of this product. But this proper installation will allow the natural rate of erosion for that watercourse crossing and allow the natural fish passage of fish migration through the structure. A quick comparison between the two products. I'm only going to compare it to a CSP because of the size of the product. The largest size of this product is about 2,100 mils. So it's most comparable to a culvert of similar size. And for simplicity, that's the most direct application of this tool. The weight is very lightweight. You can move these sections and place them in hand with two people versus slinging in some large diameter corrugated steel pipe. The cost of installation is actually less than a properly installed CSP, and I attribute that to the reduced requirement for the compaction equipment required for the proper installation of that. The compaction around the EnviroSpan, as you'll soon see, is quite minimal. It's resistant to corrosion. versus CSP will deteriorate. Leaching is non-existent. The strength is comparable. The integrity is very good. It's resistant to cracking and breaking. The only downfall of this particular product is with regards to UV radiation. If it's exposed to sun, it does have, it can deteriorate. But given that it's installed underneath the road, that's a pretty minor problem. It's resistant to abrasion, and as I mentioned, the slope is basically unlimited. Whereas with a CSP, you know, if you're anything higher than 3.5% gradient, you're getting into some very interesting fish baffles and that sort of thing. So that's no longer required. And a big part of this is the riprap placement and kind of the creation and emulation of the stream bed is very easy to do. As you place these sections in place, you can do all that in stream or in the dry work without too much difficulty. Whereas a CSP, as you can imagine, sending guys inside to place riprap is not a very fun chore. So let's hone in on our case study here. Let's go to Walton Creek. This is a project I completed a few years ago. It's located 21 kilometers west of Sundre, Alberta. The watercourse is a tributary to Bearberry Creek. It's a small permanent fluvial water body with an average bankful width of 2.4 meters. On the right, you can see our disposition, the road disposition in relation to the watercourse and the subsequent watercourse crossing that is at the intersection. If we were at the planning stage for this roadway, nowadays one would encourage that intersection to be more representative of 90 degrees, thereby reducing the length of the watercourse crossing. Having said that, for this project, we're not into rebuilding roads. Rather, we're just going to replace the watercourse crossing. But if you did have a project where you were in the planning stages, do keep that in mind with your watercourse crossings. Some of the existing culvert characteristics include the inlet end, where some ripping and cutting of the structure was observed, so some exterior damage. There was some minor erosion present, again, likely as a result of that damage to the inlet end. The outlet end, there was a significant amount of road subgrade that had washed away, creating a cliff-like situation, so to speak. The outlet end of the culvert was elevated or perched by better than half a meter. The scour pool was approximately 1.18 meters in depth, so a fairly significant pool. Overall, the culvert was a 1,000 mil culvert with 17 meters in length. It was partially collapsed, most likely due to poor installation practices and trafficking of equipment over top of that structure. We figure kind of had the banana effect going on. The culvert was not at all embedded. There was no substrate inside, and the horizontal gradient for this culvert was more than 7%, causing increased water velocity. Here's kind of the sketch of what the existing facility looked like. We have that culvert at a significant angle. We have some fairly steep slopes kind of on the shoulders of our road, in particular on the outlet end, which were eroded. The biggest take-home message from this slide that I always like to point out is on the left, on the far left side, you can see that red kind of dotted and hashed line. That's a PLA, so a pipeline. It's fairly standard under the Public Lands Act to have your dispositions adjacent to each other, and that does in fact make plenty of sense from an ecological and fragmentation perspective. But it does incur some challenges for watercourse crossing replacement projects and restoration. As you can imagine, some of these crossings were trenched in, so before horizontal directional drilling was a common practice, which means that this pipe is likely not that deep. So if you require the removal of fill over top of a pipeline, in particular if it's active or operating, that's generally frowned upon. So that's something to keep in mind with these projects for sure, is who's beside you, who's your neighbor. and what other obstacles you might have to overcome to complete your work safely. This is that inlet end. You can kind of see it's bent up and cut off. It looked like somebody had taken the oxyacetylene torch and chopped off the end. Our guess is it was maybe as a result of trenching activities for that pipeline that was installed on this side. We don't really know that, of course, but that's kind of our only theory with that. Here's a view kind of from the top looking down at the inlet end. You kind of see a bit of a dog leg in that water course. The alignment isn't exactly where it should be, but it is what we have to work with. Here's that outlet end showing the hanging culvert by approximately 1/2 meter and that very large scour pool, creating a fabulous place to go for a swim on a hot day. Here's the shot from above looking at that outlet end, and what you see in particular on the right, that the road subgrade has eroded to a point where it's encroaching onto the road running surface. As you can imagine, that creates a fairly significant safety concern. So it was definitely time for this one to have some work completed on it. Some of the fish species that were brought up by the AEPE Fish and Wildlife Internet Mapping Tool included brook stickleback, lake chub, long-nosed dace, white sucker, and a stocked inventory of brown trout. The RAP, or the restricted activity period, for this water course is September 1st to April 30th. And as you may or may not know, the RAP is the designated times of the year where in-stream work should be avoided to prevent impacts to fish during sensitive life stages, such as migration, spawning, egg incubation, and fry emergence. So avoid the RAP whenever possible. The proposed culvert replacement included maintaining the stream flow, facilitate the natural stream alignment. So if any slight corrections could be made with this work, and do our best to accommodate that, minimize the amount of in-stream work, and of course, minimize the amount of turbidity, minimize the road closure of this particular disposition, which is always an interesting one. The majority of this work was completed on the weekend. All road users were notified, and plenty of signage did go out at the beginning of this road. But one thing I noticed was that when you close the road on the weekend on the east slopes, the larger the fifth wheel, the larger the negative vocabulary. Having said that, we did complete the project and were able to let the campers through as quickly as possible. We also wanted to increase the diameter of the replacement culvert to accommodate the flow as indicated by some of our modeling associated with this watercourse. Wanted to remove that steel CSP and not leave it in the road bed. We wanted to complete our work outside of the RAP. Here's a sketch of our proposed culvert replacement utilizing our EnviroSpan modular culvert. Again, we're set back from that pipeline and we're not removing any material from it at this point in time. And the road alignment on that slightly longer EnviroSpan crossing is shown here. We'll also improve the erosion on the outlet end by changing the slope of that, by extending it just a little bit more and revegetating it as required. The first step is to remove and excavate the soil for this road. For this project, we reallocated approximately 1,200 cubes of material in aggregate, and this was stockpiled on both sides of the watercourse crossing. For water management, our work area was to be isolated from the watercourse with steel plate dams. Turbidity monitoring was completed at 12 locations, and this was done before, during, and after construction. This was tested at least twice a day, and several precipitation events occurred for the length of this project. Again, kind of highlighting the importance for your background monitoring stations, just so you have equivalent turbidity readings to compare to. Here we are excavating the road subgrade material, piling it on the one side. That's the 1,200 cubes I referred to earlier. Next, we're installing the steel plate cofferdams. This is on the inlet end. This is in preparation to put our workspace into isolation from the watercourse. Here we are kind of sizing up the alignment of our new crossing in relation to the old one, and get a feeling for where the newly soon to be constructed stream bed will set up here. And here we are excavating more material to create that stream bed. We decided to use the digging bucket here for this size of arch, just because the cleanup bucket was too large. And yeah, step number 2 is the footings. So the best footings for this this structure, as recommended by the manufacturer, are flexible and allow for movement. As I previously mentioned there, this plastic is designed to bend and to be flexible. It's designed for this type of environment where you have a lot of freeze and thaw cycles and frost heaving, as you can imagine, as you would adjacent to a watercourse. That this is really what this product's meant for. So when it comes to footings, it's really flexible is the recommended for sure. It could be something as simple as locally sourced logs from the adjacent timber stand. In our example, we use pressure treated poles. There are other options out there, including concrete grade beams, precast half cylinder grade beams, or concrete filled steel pipe. Those have all been used, but as I mentioned, the manufacturer really prefers something more flexible to allow the structure to move underneath. Now, you may have some projects where you might be regulated by other legislation or other requirements, where this structure may have to be on something more permanent. No, that's not the right word. More solid, that might not allow for flexibility. Something like a paved road surface, for example, you might not have that option to maintain that level of flexibility in your subgrade. So here we are laying out the footings. We have pressure treated poles on the bottom, and we're continuing to excavate our stream bed. I won't go into depth in the stream bed creation and emulation here in this talk, just simply because there's another talk about emulating stream bed and stream bed creation coming up. So I'll leave that good material for that talk. But that's essentially what you're doing here, is recreating that stream bed. Often when we're doing these, we find the original stream bed adjacent to this watercourse crossing, and we can tell that based on the sediments and the organics and the aggregate profile of the soil as we excavate. So most situations we're able to place this right on or very near to the original stream bed for the watercourse crossing. Here we are continuing the excavation, laying out our newly created banks for the footings, and we'll work up towards the inlet end of this particular structure. Here we are sizing the placement of the footings in our newly created stream bed. Like I say, these pieces are very maneuverable, and you can slide them up and down the footings without too much difficulty. Here we are with our footings laid out. Now, the modular culvert assembly, these structures are modulars that are 2,150 mils across. So that's the opening is 2,100 mils, and the width of these is better than 1,000 mils. The weight of each of these is approximately 64 kilograms, and our designed length was 18.2 meters. Therefore, we required 17 modules placed to get our watercourse crossing length. The placement of these are fairly straightforward. You can sling them into the excavation using an excavator or another type of machinery, and then you can remove them by hand. It's fairly straightforward, as you saw in a previous slide. And then there's slide connections that sit on top of the flanges to hold the modules together. Basically cover the entire structure with a geotextile and install the riprap where required. Here we are placing the modules on top of the footings. We slung in a package and basically pop them apart, start laying them down. Here's a slinging in package of the modules. And here are the collars or the link modules that connect the different modules together. And they just sit on top. There's no hardware or nuts and bolts to strap together. They simply just sit on top, and the mass and the weight of your subgrade is really what holds everything together. Again, some more linking with the full structure totally linked together here. Our 18.2 meters, everything is ready to go. Here's another shot of it in relation to the road subgrade and subgrade material on this particular watercourse crossing. Here we are covering the structure with geotextile. There's no recommendation whether you use a woven or non-woven geotextile. They just recommend covering it. Step 4 is the backfilling and the purge. Backfill is recommended with simply hoe tamping the soil. For this example, we did utilize the portable kind of hand tamper. However, it wasn't really required, as we found later on. And as the manufacturer stated, there's no requirement to reach proctor density with your subgrade or even 90% proctor. It's just not a requirement. Too much compaction with this structure could result in collapse of the structure from the outside inward. So that's why they recommend simply just a hoe tamp. We backfill this structure in 15 centimeter lifts on either side, being fairly diligent to fill up either side sequentially. If you place too much soil on one side than the other, you actually end up moving or pushing the structure out of alignment, which would be less than ideal. You want to make sure you have greater than 1 meter fill over top of this structure before you reach your road running surface. Purge, this is referring to the watercourse. So now that we've created a new stream bed, we want to make sure that we don't have any sediments or any source points for sediment release into our watercourse. So we actually purge our stream bed and remove the water appropriately away from the creek, just to decrease your water turbidity even further so you don't have any exceedances. Here we are with the backfilling. You want to use a material that is suitable to backfill. So what that means is basically nothing that's sticky, wet, and sloppy. You want to use ideally a good structural material that is nearby. If you are excavating one of these and you end up into some of that liquid soil, you definitely don't want to be backfilling with that just because there's no structural integrity there whatsoever. So you want to find the good stuff and place that adjacent to the structure and backfill sequentially either side in approximately 15 centimeter lifts back and forth. Here's a picture of that tamper. We ran it basically real quick along both sides. But as I said before, it wasn't really required for this particular job, and we actually haven't used it on any others after this one. It just wasn't necessary. Here we are commencing the purging of the newly created stream bed. Again, removal of any fine sediments that might be in there and removing those away from the watercourse just so that we don't have any increases in turbidity that will be unwanted. So removing that dirty water and disposing it into the forest while maintaining our watercourse flow. Here is the inlet end of the culvert. Once we were satisfied with our turbidity readings from the newly created stream bed, we were able to flip our watercourse over to the new structure, thereby discontinuing the old structure. As you can see here, our watercourse is now entirely flipped over to the modular open bottom culvert. Step 5 is the removal of the structure. Now, when removing these things, safety is definitely paramount. If possible, separate these sections in smaller pieces for easier removal. Even though it may look like there's no debris or sediment inside, there's always a likely chance that they are stuck in the riffles and whatnot. So when you remove these structures, you want to make sure that you're not picking it up and dumping that junk into the creek. You want to be pulling it out in sections and pulling it back towards you. Here we are doing that. We've separated the original structure and pulling out sequentially away from our watercourse and crushing the material for disposal and recycling. Our backfilling activities continue, reaching further to the surface of the structure in sequential increments. More backfilling, as you can imagine, takes a while to backfill 1,200 cubes appropriately. Step 6 is the reclamation. Some of these details include maintaining that 2-to-1 slope on the road structures to accommodate revegetation, placement of topsoil. If you have any, you want to make sure that you distribute it properly and to your best advantage. Seed the disturbed soils with a native seed mixture. Aprons on both ends were completed with Class 1M riprap, and complete your final water monitoring activities throughout the project. Here we are kind of putting that soil back together, finishing our 2-to-1 grades, installing our Class 1M riprap apron on the outlet end. Here's our apron on the inlet end, running right up to that road surface. And the final cleanup activities, you can see here some of the aggregate material that we salvaged from the original operation is still readily available to bring across, and we always try to bring in a load or two of new aggregate to finish the job off. Here's our inlet end looking down. So if you remember the other photos, the previous photos of the inlet end had a bit of a dog leg. We kind of tapered that out a little bit here with this new installation, just simply by realigning the new facility and the new structure. Here's a shot of the inlet. This is the outlet end looking up. This is the stream bed kind of finished with the water flowing together. You can see our riprap on either sides of our new stream bed and banks. And here's a shot of the end, so moving out the equipment at the end of the day after everything is seeded. Follow-up visits, field inspections are recommended annually. Traditionally, we use the GOA inspection forms. Now we have an app that's available, a GOA app. We'll probably be looking into its use to see if it's appropriate to accommodate for these newly restored crossings here this year. But traditionally, we do use the GOA form. Other crossing details include maintaining the road running surface condition, monitoring the abutment condition, monitor the vegetation recovery, keep an eye on your bank full width, both up and downstream at every inspection, just to see if there's much change there. Monitor the riffle crest near the outlet end, just to see if there's any movement there, as well as in this particular case and many others, we want to monitor the condition of that pipeline crossing. If we see any erosion that perhaps is being accelerated for whatever reason, we want to make sure that we're reporting that appropriately. Natural rates of erosion can be expected, but if there's anything that is less than ideal over pipeline crossing, definitely want to pass that information on. Here's a follow-up 4 months after the work is completed. You can definitely see how our stream velocity is decreased. Outlet end, 4 months after project completion, returning fish passage to the structure. Here's 1 year after, very similar fish passage, and the emulated stream bed has been returned to this section of the watercourse. Here's the inlet end. You can see we do have some natural rate of erosion as that watercourse continues to correct itself over time, as it has been interrupted by a failed crossing for a number of years. 2 years after, not much movement at all. The watercourse is still flowing, and we still maintain that fish passage to its advantage. All right, we're going to wrap it up here. I'm sure you're all eager to ask me plenty of great questions. The modular culvert system is suitable for watercourses with steep grades, replacement of hanging culverts on resource roads. It can be used both for a permanent and temporary installation. It can be utilized both on fish and non-fish bearing watercourses. It is a great option where deep excavation is not suitable. For example, if there's a pipeline and pipeline right-of-way adjacent to your disposition, then it can be installed on saturated organic soils. There's a few different tricks when it comes to the installation of this product in those situations, but we can save that for a different presentation. And it is unsuitable in a couple cases where I would not recommend using this particular structure. Those would be in watercourse crossings requiring an opening greater than 2100 millimeters, or if you have low profile roads, I would not recommend this as well, because you do need to maintain 3 feet or better of cover above the structure, and just to maintain structural integrity of the system. All right, any questions?
All right, thanks, Ben. So I see a couple of questions are starting to come in. Just to give people a couple of minutes to do that, we have a little poll that we put out every webinar just to see everyone's affiliations. So I'll launch that now. You should be able to answer just by clicking on your window there. I know some people have had some issues with it, so I'm hoping it works. To answer one of the questions that have come in, someone is asking if they can get a copy of the presentation. So the recording of the presentation and a transcript of the Q&A portion will be distributed to everybody who has registered for the webinar. So we have everyone's email addresses, and we'll be distributing that information that way. Eventually, all of this will be available on the awccc.ca website, but we're still getting that set up. So for now, it will be distributed by email. All right, so we'll close this. So today, looks like we have an even spread between consulting and industry, so that's good. All right, so we'll jump into these questions. So the first question is, what is the typical cost of an installation like the one presented in the case study?
Yeah, that's a pretty common question. As you can imagine, there's numerous variables that come into play there. Obviously, the amount of material over it, the location of it, and of course the product used. I think the cost for this one, I think we were around the $80,000 mark for this particular job, kind of all in sort of thing.
All right, we got another question that was asking about cost, so we'll just go straight to that one. How much was the arch specifically in that installation?
This particular one, I can't remember the exact number. I've installed quite a few, and I wouldn't want to take the thunder away from any of the suppliers or anything. I'm probably not the right guy to get pricing for those pieces. Like that would be more of a Nilux or somebody else question for them. It is more than a CSP for sure. Obviously, it depends on a lot of factors, including the size of the CSP, the thickness that you're going with. Like I mentioned before, the cost savings really is what we found. It comes around with the installation. So up front, just the structure alone, it is more than the CSP for sure. Depends on size, sometimes double, sometimes less. But at the end of the job, you're actually even or even saving a little bit of money just because of the installation being a little bit different. Especially if you have a good crew. If you have a crew of guys that have installed these before, you know, a lot of times, a lot of field people agree with me on this one. It's not the rate, the price tag per hour for the equipment actually has everything to do with the guy sitting in the seat. And he's the guy that's really going to help you along with this project and maximize and capitalize on those cost savings.
All right, thanks. So the next question is asking, you said that UV can degrade the material. Are you concerned with the ends of the structure that are exposed to the sun?
Yeah, no, that's a fair question for sure. Because the structure is sitting on the log footings, in this case, it's pressure treated logs. There really is no buoyancy effect of these, you know, like you do with the culverts. There's no very little uplift. Now, if you had your modules extended so far out that there was nothing sitting on top of them, that would definitely be a factor. But you know, you're also asking a question here with regards to proper sizing. I mean, yeah, I guess if you improperly size the structure for your water course and your stream is flowing at maximum or over maximum capacity, you're going to run into issues, but you're also going to run into issues with several other things. Under expected conditions, with the footings in place, with proper placements and construction of this, I'm not concerned with buoyancy on the outlet or inlet ends.
Thanks for that. I think another concern was the UV degradation of the material itself. So you said that the plastic does degrade with sunlight. So just asking about how the ends of the culvert will stand up to the sun because they're exposed a little bit.
For sure, yeah. So the whole structure is wrapped in the geotextile,
right? Okay.
Which does help, but that's still not the complete answer to the question. Let's so yeah, it does degrade. That's more of a point of concern with storage of this material. If you had a lot of this material, you wouldn't want to leave it outside in a yard uncovered. The outlet ends, what is exposed, are not taking really much weight. There's a bit of weight to the road there, but it's not like those pieces are taking the mass of the trucks and the vehicle traffic. So it hasn't been a problem yet.
All right, thanks. So for the purging of the new installation, how long did that process take?
We purged this one, and we usually try to purge it for, I would say, about a whole day, at least a whole day. Yeah, just it depends a lot of what is in that stream bed. For example, if you have silt, as you can imagine, silt and sand would fall out of the water column a lot quicker than the clay well. It's kind of like doing a hygrometer test on soil. It takes quite a long time for that clay to fall out. So if you do have a lot of clay, I would suspect that you could be easily longer than a day to purge that water course for sure. This one was about a day.
All right. The next question. Are you aware of any situations where this type of product has been installed and failed structurally?
Good point for sure. I am not aware of anything, but it's definitely a concern for sure. There have been all sorts of load testing completed on this product to provide some backing and encouragement and support for the structure. So no, I'm not aware of anything, but there's definitely documented, signed and stamped load test ratings for this particular product under different situations, and of course it is engineered, approved by an engineer and all that good stuff. So yeah, in fact, there is quite a bit of material out there with regards to well, how much material can you place on top of this? And in the literature and some of the load and strain tests that have been performed, They have looked at mining situations where the load on top of the structure was, don't quote me on this, but I believe there are situations 50 to 80 feet of subgrade material, and it has not yet caused any failure of the structure itself. So yeah.
All right, thanks for that, Ben. So we're coming up at the 2 o'clock mark, and I don't see any new questions coming in. So yeah, I guess we can wrap things up. So I'd like to thank today's presenter, Ben Poltorak. Thank you to everyone who attended the webinar, and we hope that you will join us for some of the other presentations over the next 5 weeks. Our next webinar in the series is taking place next Tuesday, June 2nd, where we'll have Paul Harrington from AER giving us a presentation on roadway watercourse crossing management in the Boreal region. So if you enjoyed this webinar, I encourage you to have a look at some of the other webinars scheduled as part of the series on the GoToWebinar page, as well as on the awccc.ca website, and register for some of those other presentations. So I'd like to say thank you again to Ben for presenting to us today, and I hope to see all of you attending some of our future webinars. Stay safe and have a great day.